Hey, welcome to the Explainer. Today, we're going to dive into a single beautiful equation that totally changed how we see the universe. It's an incredible story about a secret code hidden in starlight and the genius who finally cracked it. So, for centuries, right, we looked up at the stars and they were just tiny lights. That's it. But what if they were sending us a message? You see, as our instruments got better, we started to realize that their light wasn't just light. It held patterns, almost like a language. The only problem? No one had the dictionary. So, flash forward to the early 1900s. Scientists could now take starlight and split it open, kind of like a prism, into what's called a spectrum. It's like a rainbow, but with these mysterious, dark lines cutting through it. And they noticed something really interesting. Different stars had different patterns of lines. These were like cosmic fingerprints. But what did they mean? What were the stars trying to tell us? This all boiled down to one huge question. What are the stars actually made of? I mean, really. The going theory back then was, well, kind of simple. People figured stars were probably made of the same kind of stuff as our planet Earth. It makes sense, right? Except it was completely, totally wrong. The real answer was way stranger than anyone imagined. And the key that unlocked this whole mystery, it came in 1920 from a young Indian physicist named Meghnad Saha. And get this, he wasn't some famous astronomer staring through a giant telescope. Nope. He was looking at the fundamental physics of superhot gases. And his work was about to become the foundation of modern astrophysics. What Saha did was just brilliant. He created this equation that cleverly mashed together two super powerful fields of physics, quantum mechanics and statistical mechanics. The result was this incredible new tool that could describe with perfect mathematical precision exactly what happens to atoms when you crank up the heat to, star-level temperatures. Okay, so how does this thing actually work? To really get why Saha's breakthrough was such a big deal, we need to quickly break down the three main ideas his equation juggles: temperature, pressure, and this thing called ionization. First up, ionization. So what is it? Just imagine you're heating up a gas. Hotter, hotter, and hotter. The atoms start zipping around so fast and violently that eventually, bam, their electrons get knocked clean off. At that point, you don't really have a gas of nice neutral atoms anymore. You have this superheated mess of positively charged ions and loose electrons. And that state of matter has a special name: plasma. Saha's equation is basically a recipe. It's a formula that perfectly balances these three key ingredients. You tell it the temperature of the gas, you tell it the density, like how crowded the atoms are, and you tell it the ionization energy, which is just how much of a kick an atom needs to lose an electron. You plug those in, and the equation spits out the answer, exactly what percentage of those atoms are now ionized. And here's where the magic really happens. This equation basically gave astronomers a cosmic Rosetta Stone. It was a reverse translator. For the very first time, they could look at those weird spectral lines from a star light years away, that message we were talking about, and they could work backward to figure out the exact temperature and pressure in that star's atmosphere. This was a total game changer. All right, so now scientists have this amazing new tool. The really interesting part is what happened when they started using it. They could finally decode those messages from the stars. And let me tell you, the results were shocking. Physicists like Ralph Fowler and Edward Arthur Milne jumped on Saha's work right away. They got it. As Milne put it, they realized the strength of those spectral lines wasn't just about how much of an element was in a star. It was all about temperature. If it's too cold, the atoms aren't excited enough to make the line. But if it's too hot, all the atoms are ionized and the line disappears too. It had to be just right. This insight let them nail down the conditions on stars with unbelievable new precision. And this leads us to the incredible Cecilia Payne. In 1925, as part of her PhD thesis, she took Saha's equation and all these new refinements, and she just painstakingly applied them to the light from star after star after star. She was about to completely rewrite our map of the universe. In her discovery, kicked off a scientific revolution. That old idea of stars being like Earth, it was completely blown out of the water. Payne's math showed, with zero doubt, that stars are nothing like our planet. In fact, they're made almost entirely of the two simplest, lightest elements there are: hydrogen and helium. I mean, just look at these numbers. It's wild. Something like 91% hydrogen, almost 9% helium. And all the other elements that make up you, me, and our entire planet, the oxygen, the carbon, the iron, all of that is crammed into that tiny little 0.1%. It's basically a rounding error. Thanks to Saha's equation and Payne's brilliant work, we finally knew what the cosmos was actually made of. But the story doesn't stop there. The power of Saha's equation isn't just about looking at stars today. It actually lets us peer back in time, all the way to the very beginning, and understand a supercritical moment right after the Big Bang. See, right after the Big Bang, for the first few 100,000 years, the entire universe was this incredibly hot, dense soup of ionized particles, a giant ball of plasma. And because of all those free electrons zipping around, it was totally opaque. Light couldn't go anywhere. It was like being in a super thick fog, constantly bouncing off of everything. So the big question is, when did the fog clear? When did the lights turn on in the universe? Well, Saha's equation gives us the answer. It predicts that as the universe expanded and cooled down, it hit a magic temperature, about 3,000 Kelvin. At that exact point, it became cool enough for all those loose electrons and protons to finally get together and form stable, neutral hydrogen atoms. This moment is called recombination, and it was a huge deal, because as soon as those free electrons were locked up inside atoms, poof, the fog cleared, light was suddenly free to travel across the cosmos without bumping into anything. And the very first light that was set free at that moment, it's still traveling through space today. We can see it. We call it the cosmic microwave background. It's literally the oldest light in the universe. So when you step back and look at the whole story, what's the real legacy of Saha's work? It is just this perfect example of how one profound idea in physics can ripple out and change everything, connecting the hearts of stars to the very birth of the universe. Think about it. This one equation solved the decades-old mystery of what those lines in starlight meant. It revealed the true composition of not just stars, but the entire universe. It even explained a crucial event right after the Big Bang. And today, it's still a foundational tool in astrophysics and plasma physics, all from one idea. And that just leaves us with this final thought. Saha's equation found an entire universe of information hiding in plain sight, in a simple beam of starlight. It really makes you wonder, right? What other cosmic secrets, what other huge truths are out there right now, just hidden in plain sight, waiting for the right person to come along with the right equation to unlock them all?